So now we're going to talk about reasoning with no information, which is just total blasphemy at an engineering school. But we're going to see that it's actually possible, and it does a very good job in many examples. So for reasoning with no information, we're going to talk about Fermi estimation. So Enrico Fermi was a physicist who was also involved in the Manhattan Project, and he's very famous for coming up with really quick estimates that are correct to the order of magnitude, meaning that if you just want an estimate that just has the correct number of digits, if that level of accuracy is okay, without any information, you can actually get such an estimate. So some of these questions are practical, some others are just fun. So we're going to see both practical and fun questions. Maybe starting with fun questions first. So when he was working on the Manhattan Project, apparently when some atomic explosion was being tested, when the test was being conducted, he was in his office, which was not that far away, and he just dropped a few pieces of paper and then measured how long those pieces of paper traveled, maybe 20 centimeters or something like that. And based on that measurement, he got an estimate of the power of that nuclear explosion. And then when they actually did the calculation, his estimate was remarkably close to the correct value. It was correct to the order of magnitude. So if the true number was, I don't have the numbers here, but it was correct to the number of, to the order of magnitude. So with Fermi estimation, we always work with numbers like this, the ones you see on the screen. We have no information for answering the problem. There's pretty much nothing given. But you can see that we will come up with some estimate just using these numbers and by just multiplying and dividing them. So the first question, I think this is a famous one. How many piano tuners are there in Chicago? That's it, no information. So one way to approach this is by Fermi estimation. And for that, we need to just break this question into smaller pieces where we multiply and divide some numbers to get what we're looking for. So maybe first we can start with population of Chicago. I don't know that much about Chicago, but the population of Chicago is close to one of these numbers. So definitely more than 1, more than 10, I'm pretty sure, right? I need to stop somewhere. So this is 10 million, right? This is 1 million. This is 100,000. So which one do you think is just closer? We also have 100 million if you want. So we need to just pick one of these numbers. And the thing is actually, it's just a matter of picking the number that works better, right? So to me, this 10 million, order of 10 million, I think is just too large. And 100,000, I'm pretty sure it's too small. So order of 1 million. So it is also about scientific notation of numbers, right? So when we represent a number with scientific notation, it is some d times 10 to the power of k, where d is between 1 and 10, right? So population of Chicago, I think, is some d, I don't know what that is, times 10 to the power of 6. So if you tell me population of Chicago is some number times this, I would be suspicious. Also, if you tell me it's more than 10 million people, I would be suspicious. So I would go with just 10 to the power of 6. So our estimate for number of people in Chicago, 10 to the power of 6. Then we can think of number of pianos per person. So again, we can have some feeling of this number, right? Based on how common or how unexpected having a piano is. So, well, this means every single person has a piano. So I think this is pretty clear this is too large. 1 piano for every 10 people. 1 piano for every 100 people. 1 piano per 1,000 person. So I think 1 piano per 1,000, if it is true, then having a piano is just such a shocking thing that people would just talk about it. They say, wow, I've seen a piano in their home, right? And so I'm a bit skeptical of this. This one piano per every 10 people. Well, the thing is, average size of a household is I think something around 4, maybe between 3 and 5, let's say 4, right? So to me, this is almost saying the same thing as 1 piano per each, one out of 2 households has a piano. So that seems to be too many, right? So I think this is the best option out of this limited choices that we have. And actually, the fact that our choices are limited makes it even better. That's the interesting part. So number of pianos per person, 10 to the minus 2, meaning one piano per 100 residents of Chicago. All right. So then we can, we can think of, maybe how many times each piano needs to be tuned per year. So I'm trying to get closer and closer to the number, which is number of piano tuners, right? So how many times do we need to tune a piano per year? And these are your options. This means tuning a piano every 10 years. This is tuning it every year. This is tuning it 10 times per year, 100 times per year. So what do you think? Which one? So this, tuning a piano once and then just using it for 10 years, this seems very odd to me, because it means a pianist in their lifetime, they just see their piano being tuned just 4 times during their, let's say, 40-year professional career. So this is definitely too small. I would say tuning 10 times per year is something like tuning pretty much every month. So this also seems quite a lot to me. So I think this is the best number, the most suitable number. So the number of times that a piano is tuned per year is 1, or 10 to the power of 0. All right. Well, then based on these, pretty much we have an estimate of how many pianos are there in Chicago in a year to be tuned. How many piano tuning tasks are there in Chicago in a year? It's 10 to the power of 4. So there are 10,000 piano tuning tasks in a year. Now that we know what is this total number of tasks, we can think of how many pianos one piano tuner tunes per year for their job to make sense. So, because then if we just divide it by this, we get the answer, right? If we divide 10 to the power of 4 by how many pianos one piano tuner tunes per year, we get the number of piano tuners. So, all right, well, if one piano tuner only tunes one piano per year, I think it doesn't make sense, right? Because we can also think of how much time, it takes to tune a piano. I think maybe a couple of hours. So definitely it doesn't take 1 year. 10 per year, this also seems a bit unusual. 100 per year, or some number times 10 to the power of 2, this makes some sense. And this one is 1,000 per year, right? So it's like in a year we have around maybe 250, 260 working days, right? 1,000 means every single working day they have an average of 4 pianos to tune. So this is also a bit too much, considering that these people need to move to different locations. The transportation takes time. People work around 8 hours per day, right? So this doesn't work with what we consider as a normal job, right? This doesn't work. This is just too few per year, just 10. Let's go with this. So number of pianos tuned by one piano tuner per year, 10 to the power of 2. So now if we just do some simple multiplication and division, we will get the answer. So there are these many people in Chicago. When we multiply this to this, as this is per person, so we can just look at the dimension of these things. This is number of people. This is pianos per person. So multiplying this to this tells us how many pianos there are. Then this is per year, right? So multiplying this to this to this says how many tuning jobs there are. And then when we divide it by this, because this is, again, per year, we're going to get the result. So this times 10 to the minus 2 times 10 to 0 divided by 10 to the power of 2. So number of piano tuners in Chicago is some D times 10 to the power of 2. D is some number here. Between these numbers, the kind of expected value, the sort of like average number to think of is like 5, right? But we don't care about D in this method. We only care about the power of 10. So around 100. So you saw that we came up with some estimate of number of piano tuners in Chicago without any information. Sorry? K? K is the power of 10. We always look for K in Fermi estimation. So when we have a number, if you want to represent it using the scientific format, we represent it by some value between 1 and 10 times 10 to the power of K, right? So here with Fermi estimation, we only care about this, but this value doesn't just represent 100. It represents something times 100. And the thing is, if you check the occupational data in Chicago, you're going to see that actually the number of registered piano tuners in Chicago is very close to 100. And we only wanted to be correct to the order of magnitude. So here, our estimate is good enough. If something that is in the order of 100, we estimate the order of magnitude correctly. So this means that this Fermi estimation is correct indeed when we check the occupational data. Any questions? All right, so let's move on to the next question. This is also a famous example. How many golf balls can be fit in a Boeing 747? I've heard that some people ask questions like this in data science interviews. So if you're interested in data science, maybe you need to use Fermi estimation just for the sake of passing some interviews. But I think it's also useful elsewhere. So how many golf balls can be fit in a Boeing 747? So from an engineering perspective, the answer is I don't know, unless we have information about the dimensions of the Boeing and the packing number of golf balls, the exact geometry. Here, I mean, this is meant to be a totally empty Boeing 747, right?
In terms of width or volume?
Sorry?
Like in terms of width, it can fit, or in terms of...
In terms of volume, yeah. Golf ball is 3D, and the Boeing is also 3D. So again, we have those numbers, right? 10 to the minus. So we always work with these numbers. And more numbers if needed, but powers of 10. So, all right, let's start with the Boeing. So let's first estimate the volume of a Boeing 747, and then estimate, kind of work our way from there. So sorry to all the engineers. A Boeing 747 to me looks like this. So I just assume the sort of a cubic shaped Boeing. So volume of this airplane. All right, I just need to think of an airplane. All right, so when I'm inside an airplane, I guess a Boeing, which is not that huge. When I'm standing, right, the ceiling is not that far up, right? So for the height, I need to come up with one number. So let's say we're working based on meters, based on the metric system. So height of the room inside a Boeing, I need to come up with one of these values. 1 meter, well, I certainly fit in it, so this is not good enough. But 10 meters, well, it's a matter of which one is closer. So 10 meters is really tall, right? I'm not even sure if the ceiling here is 10 meters. Maybe it is. But in an airplane, definitely it's not like this, right? So I would say actually between these two numbers, to me, this makes more sense. I feel like it is something like 3 meters or something like that. So as this is 1 and this is 10, I'm thinking of 3, but I should not use 3. That's the interesting part. I should just pick one of these given options. So I would use this. Although that I know that it's larger than 1 meter, this makes more sense than this. And the thing is with Fermi estimation, these sort of overestimation and underestimations kind of cancel out with each other because we are kind of, we are very relaxed about these numbers. So sometimes we pick something that is a bit larger, sometimes something that is a bit smaller. And as long as these errors are not all in the same direction, then our estimate would be good enough. So let's say, so this is h, so this is length of the airplane. So again, between these numbers, 1 meter, definitely not. 10 meters, 100 meters, or 1 kilometer. So I think 100 meters makes some sense because, I mean, when you're on the tarmac, it takes a while if you want to go from the tip to the very end. So for L, let's consider 10 to the power of 2. And then for the width of inside the airplane, well, I mean, I'm not exactly sure about that model, but to me, the width is a couple of meters because people just move to the other. I mean, even if it is just a narrow airplane, I don't think the 747 is a narrow airplane. It has, I think, a couple of aisles. So I mean, I'm not really, going without any information. Like I have a sense of a piano, I have a sense of a Boeing 747, right? So it's not like the tiniest airplane, but it's not that huge either. So my impression is that it has more than one aisle. So then I would say the width of inside the airplane would be a couple of meters. So what do you think? This or this or this? So what is the volume? So volume of a cubic Boeing 747 would be 10 to the power of 0 times 10 to the power of 2 times 10 to the power of 1, so it's 10 to the power of 3. So in cubic meters. All right, so a golf ball. Well, I mean, one way to approach this is calculating the volume of a golf ball, but there's also an alternative here. The alternative is like imagining the space of 1 cubic meter. So I guess something like this is 1 meter, right? So some cube that is maybe, you know, takes this much space is 1 cubic meter. So now I can just think of how many golf balls I can fit in that cube, and then that allows me to just, you know, multiply to this and get the answer. So I think the diameter of a golf ball, I'm not sure, but I think it should be something between 3 and 4 centimeters, right? Something like that. So, and then we don't want to be exact. That's the advantage. If we were solving this as a mathematics problem, we also needed the packing number of that shape, but, you know, because they don't just fit, you know, with perfect geometry, with perfect symmetry. But I'm just assuming that if I have 1 by 1 meter, I want to just, you know, fill the ground level of that cube, you know, these, as there are the diameters is 4 centimeters, I can have something around, I guess, this is 1 meter by 1 meter, I can have 25 by 25 golf balls, right? So I think the number of golf balls that I can fit would be 25 times 25 times 25. So what is that number? 625 times 25. So it's 15,625. But then I'm not going to use it for the problem. I'm going to pick something from here. So 15,625. It's here, right? Because it's 1.5 to the power times 10 to the power of 4. So this is when I went with the diameter of 4, but you may say, no, a golf ball is smaller than diameter 4 centimeters, it's 3 centimeters, right? If it is 3 centimeters, I'm going to get 33 here, 33 here. So the number I'm looking for, I think, would have the same order of magnitude. Let's see. Yeah, 33 to the power of 3 is this, right? 25 to the power of 3, it was So the thing is, you can see, regardless of, you know, whether we go with 3 centimeters or 4 centimeters, it doesn't matter, because we arrive at 10 to the power of 4. And then I'm going to consider number of golf balls in a unit cube of 1 cubic meters. So this is 10 to the power of 4. So we just multiply this number. So what we're looking for, the answer to the question is 10 to the power of 3 times 10 to the power of 4. So it's 10 to the power of 7. And then some people have actually calculated the volume of inside the Boeing 747 and exactly the volume of a golf ball and the packing number and everything. And the true answer, based on exact volume, the true answer, let's call it ground truth, is 1.7 times 10 to the power of 7. So for our purposes, this is good enough. So, I mean, some of these examples are, you know, more like jokes. I think there's another famous example about how many rolls of toilet paper you need if you want to just cover, you know, around planet Earth with toilet paper. And you can calculate it, and someone has kind of verified that by, you know, exact sort of calculations. So many of these are just funny examples just to see how we are capable of coming up with an estimate when there is no information and the question is just so bizarre. But the thing is, there's also some, I mean, there are, I think, many practical applications to this. One application that I can think of is some times ago, I was working on a project where we were trying to analyze this population, internationally mobile researchers who have some ties to Germany. So I was in a meeting, and one of my students told me about doing some data analysis, and that she got the the list of researchers. So we were working on bibliometric data, looking at affiliation addresses and how affiliation addresses change between different publications to say whether that published researcher is internationally mobile or not. So she did all that and then told me, I got the results, and there are like 1.6 million internationally mobile researchers with ties to Germany. And this number was looked very suspicious to me, because I immediately did some very quick, Fermi estimation in my head and realized that this is just such a huge number for what we should expect, because the population of Germany, I don't know the exact number, I think it's something around 80 million. But we were not really looking at researchers who all live in Germany, but within a 25 time period, also researchers who have been a visitor or have been in Germany for half a year and did some research and published with a German affiliation, they would count as well. Therefore, the population at exposure, the total population to me was something around 100 million, right? So 10 to the power of 8. 100, just a bit more than population of Germany. But then, being a researcher, how common or how uncommon is it? I think from 100 people, only one of them becomes a researcher, becomes a published researcher. So then, fraction of researchers per, probability of one random person being a researcher, this, and then probability of a researcher having international mobility. So the thing is, like, migration and mobility is a rare event generally. So most people just live in their country of birth and work there, right? So to me, also the probability of that migration was something like 10%. So something like this. Therefore, my estimates of the order of magnitude for this was something like 10 to the power of 5, just by multiplying these numbers, right? And the number we had here was 1.6 million, which is 10 to the power of 6. So this was wrong by one order of magnitude, but I could see that very quickly just by thinking of these three numbers, right? So then, I said, well, maybe you want to double check what was in the code that you got this number, because this seems just so large. And then actually, we did the very detailed analysis and everything. There was an error in the code. We fixed the error. Then at the end of the study, we measured exactly these many female researchers, female published researchers, or let's say and so we looked at their first name to predict whether they are more likely to be female or male, because we were looking at gender disparities in academia. So male and migrating researchers, and when you add up these numbers, you get this, which is 1.7 times 10 to the power of 5, right? So so you can see that this is the product of these three numbers. You can see that having some sense of the magnitude of some number is really helpful, because you can immediately see that there must have been something wrong in the calculation. So this is one practical example based on my own experience. But I think this Fermi estimation is very useful, because sometimes we just don't have any information, and it's very useful to be able to provide some estimate with some level of relevance. So hopefully this method would be useful. Any questions? All right, so this was the last lecture of the course. Thanks a lot for coming to the class. Thanks a lot for being a part of this course and your active engagement. If you have any questions, please post on Piazza, and that's it for today. Thank you very much.